This sentence is false, and your brain just experienced its first paradox. Comment, where are you watching from tonight? Because we're about to explore every mind-bending contradiction that will literally put you to sleep. The liar paradox. Remember that sentence from earlier? This sentence is false. It just broke every rule of logic your mind knows. When you say it's true, it becomes false. When you say it's false, well, that makes it true. Your brain keeps looping endlessly, searching for an answer that simply doesn't exist. Picture yourself trapped in a revolving door that spins forever. Every step forward takes you backward. Every logical move becomes illogical. Ancient Greeks discovered this exact mental trap over 2,000 years ago, when a Cretan philosopher named Epimenides boldly claimed all Cretans were liars, ECO. But wait, if he was telling the truth, then he was lying about being a liar. If he was lying, then he was actually telling the truth about always lying. Your everyday life encounters these logic loops constantly. When someone says, "I always lie," your mind freezes. Can't believe them. That would make their statement true, meaning they don't always lie. Can't disbelieve them either, because then they'd be telling the truth about always lying. Ever notice how computers crash when fed impossible commands? Your brain does something similar, but gentler. Instead of blue screening, it enters a dreamy, confused state. That spinning sensation you're feeling right now. That's your logical mind, slowly powering down. Modern philosophers call this truth-value gaps, statements that exist outside true and false. They're like optical illusions for your reasoning mind. The harder you stare, the more reality seems to wobble and blur. Notice how your thinking mind starts that familiar exhaustion creeping in as logic collapses. Most paradoxes work exactly like mental quicksand. The harder you struggle with rational thought, the deeper you sink into peaceful, dreamy confusion. Your overthinking brain finally discovers something genuinely impossible to solve, so it simply surrenders to the mystery. Russell's paradox. Behind every library's perfect organization lurks an impossible question. Imagine you're a librarian creating the ultimate catalog, a book that lists every book that doesn't mention itself. Sounds simple enough, until you realize this catalog faces an impossible choice. If your catalog mentions itself, then it belongs with books that mention themselves, meaning it shouldn't be in your catalog. But if it doesn't mention itself, then it perfectly fits the description of books that should be listed, meaning it must mention itself. Bertrand Russell discovered this brain-melting problem in 1901 while studying sets, collections of things with shared properties. He wondered about the set of all sets that don't contain themselves. Does this mysterious set contain itself or not? Picture yourself sorting your belongings into boxes. Most boxes don't contain themselves. Your sock drawer doesn't contain another sock drawer. But what about a box labeled boxes that don't contain other boxes? If you put that box inside itself, it breaks its own rule. If you don't, it should go inside itself. Russell's discovery shattered mathematics overnight. Every logical system seemed infected with this paradox virus. Smart minds across Europe scrambled to rebuild logic itself from scratch. The foundation of all mathematical reasoning suddenly felt like quicksand. Your mind probably feels that familiar fuzziness creeping in now. That gentle confusion when logic eats its own tail. Mathematics spent decades healing from this wound, creating new rules to avoid the trap. Sometimes, the most beautiful discoveries come from finding cracks in what seemed perfect. The barber paradox. Every small town has that one barber who cuts everyone's hair. But Russell's mathematical nightmare becomes a cozy story when we imagine this barber facing an impossible rule. He only shaves men who don't shave themselves. Walk down any main street and you'll find him. The friendly neighborhood barber with his red and white pole spinning hypnotically. Local farmers, shopkeepers, and teachers all trust him with their morning routine. The rule works perfectly, until someone asks the obvious question, who shaves the barber? If he shaves himself, then he belongs to the group of men who shave themselves, meaning he shouldn't be shaving himself according to his own rule. But if he doesn't shave himself, then he fits perfectly into the category of men he's supposed to shave, which means he must shave himself. Your brain starts that familiar gentle spinning now, doesn't it? Like watching that barber pole rotate endlessly outside his shop window. Round and round, red and white stripes, blurring together until your eyes grow heavy. Some philosophers suggest the barber simply doesn't exist. The rule itself prevents him from being real. Others imagine him perpetually reaching for his razor, then pulling his hand away, trapped in eternal indecision. Picture that poor barber, staring at his reflection each morning, razor hovering inches from his chin. Logic holds him frozen between two impossible choices. The gentle absurdity wraps around your thinking mind like a warm blanket. Zeno's Paradox of Achilles and the Tortoise. Ancient Greece's fastest runner accepts a challenge from the world's slowest creature. Achilles, hero of Troy, agrees to race a tortoise, but gives the little guy a generous 100-meter head start. Surely speed will triumph over this tiny advantage, right? Mathematical logic says otherwise, and here's why your brain is about to feel wonderfully confused. Before Achilles reaches the tortoise's starting position, our shelled friend crawls a bit further ahead, maybe just 10 more meters, since the tortoise moves 1/10 as fast. When Achilles reaches that new spot, the tortoise has moved again. Only 1 meter this time, but still ahead. Each time our hero closes the gap, the tortoise maintains some microscopic lead. The distances get smaller, 100 meters, then 10, then 1, then 0.1, then 0.01, shrinking forever, but never quite reaching 0. Zeno realized something mind-bending. Achilles must complete infinitely many tasks to catch up. First, reach the 100-meter mark, then the 110-meter mark, then 111 meters, then 111.1, then 111.11. Infinite steps stretched before him, like an endless hallway of mirrors reflecting into eternity. Your daily walk to the coffee shop hides this same puzzle. To travel any distance, you must first cover half that distance, then half of what remains, then half again. Mathematics demands you complete infinite halvings before taking a single full step. Yet somehow, you reach that coffee shop every morning. Your body effortlessly solves what stumped philosophers for 2,500 years. Movement flows naturally, while your logical mind ties itself in knots. Feel that gentle contradiction washing over your thoughts. Reality works perfectly, while reason struggles to keep up. Zeno's dichotomy paradox. Getting out of bed this morning required solving an impossible mathematical puzzle, lethen, one that should have kept you frozen under your blankets forever. Every step you take breaks the laws of logic, yet your sleepy brain never notices. Before reaching any destination, you must first travel halfway there. Sounds reasonable enough. But here's where your mind starts to melt. Before reaching that halfway point, you must first reach the quarter-way mark. Before the quarter, the 1/8. Before the 1/8, the 16th. Picture yourself trying to leave your bedroom. The doorway sits 10 feet away. First, you must reach the 5-foot mark. But wait, before that, you need to reach 2.5 feet, then 1.25 feet, then 0.625 feet. The distances keep shrinking. 0.3125, 0.15625, 0.078125. Each step requires completing the previous step, creating an infinite chain of prerequisites. Mathematics insists you must finish infinitely many tasks before taking your first step. Your movement should be impossible, trapped forever in an endless sequence of smaller and smaller requirements. Yet somehow your feet glide effortlessly across the floor. Your morning routine unfolds naturally, while ancient Greek mathematics screams in protest. Zeno created this paradox 2,500 years ago, and philosophers still debate how motion exists at all. Feel that dreamy disconnect between what your body knows and what your mind calculates. Reality flows smoothly, while logic stumbles over infinite subdivisions. Your brain grows heavy, trying to reconcile the impossible math with your effortless movement through space. The arrow paradox. Watch an arrow fly through the air after leaving a bow. It glides smoothly from point A to point B, cutting through space like liquid motion. Your eyes track its elegant arc without question, but freeze time for just one instant, and motion itself becomes impossible to explain. At any single moment, not to say, exactly 3.2 seconds after release, not to say, that arrow occupies one specific position in space, not moving toward that position, not moving away from it, just sitting there like a photograph. In this frozen instant, the arrow appears completely motionless, identical to an arrow resting peacefully in a quiver. Now advance time by the tiniest fraction, 1/1000th of a second later. Again, the arrow occupies exactly one position, still motionless in that instant. Another fraction forward, same thing, perfectly still, occupying one precise spot with no movement whatsoever. Zeno realized something that makes your logical mind feel wonderfully dizzy. If the arrow remains motionless at every single instant, when exactly does movement happen? Motion seems to slip between the cracks of frozen moments, existing nowhere, yet somehow everywhere. Think about your hand reaching for a glass of water. At each microscopic instant, your hand occupies one fixed position, completely still. Yet somehow these motionless moments stack together to create fluid movement. It's like watching a movie made of still photographs. Except there's no projector to explain the magic. Modern physics talks about velocity and acceleration, but they're describing what happens between moments, not what exists in any actual instant. Movement lives in the gaps, in the spaces between thoughts. Your mind grows heavy trying to catch motion hiding between the seconds. The ship of Theseus. Your favorite childhood toy sits in your closet, but every screw, every piece of fabric, every component has been replaced over the years through repairs and upgrades. The question that will make your brain feel like warm honey: is it still the same toy? Ancient Athenians faced this exact puzzle with their most treasured possession, Theseus, the ship that carried hero Theseus back from defeating the Minotaur. As years passed, rotting planks needed replacement. Then the sails wore out. The mast cracked and required rebuilding. One by one, every original piece of wood, rope, and metal was swapped for fresh materials. Generations of Athenians gazed at this legendary vessel in their harbor, wondering, are we looking at Theseus's actual ship, or just a replica wearing the original's identity? Your own body presents this same mystery. Every cell in your skin replaces itself roughly every month. Your skeleton rebuilds completely every 7 years. The atoms forming your muscles, organs, and bones today are entirely different from those you had a decade ago. Yet you remain you. Consider your smartphone after countless software updates, case changes, and screen repairs. When does it stop being your original phone? What about your grandmother's favorite recipe, passed down through generations but modified slightly each time? Different ingredients, adjusted measurements, modern cooking methods. Philosophy calls this the problem of persistence through change. Your mind drifts gently as it tries to grasp where identity lives when everything physically transforms. The answer: feels like trying to hold water in your hands. The Sorites paradox, paradox of the heap. One grain of sand never makes a heap. Everyone agrees on that simple fact. Adding a second grain changes nothing. A third grain? Still not a heap. Your logical mind nods confidently, following this reasonable progression until something impossible happens. Somewhere between grain number 3 and grain number 3000, a mysterious transformation occurs. Suddenly, you're staring at what everyone calls a heap of sand. But when exactly did this magical moment happen? Which specific grain tipped the balance from definitely not a heap to obviously a heap? Ancient Greeks discovered this maddening puzzle while pondering everyday language. Remove one hair from someone's head, they're still not bald. Remove another hair, then another. Somewhere in this gradual process, a person with hair becomes a bald person. Yet, pinpointing the exact hair that caused baldness feels impossible. Your morning coffee illustrates this beautifully. Add 1 grain of sugar, idea, still not sweet. Add another, then another. Grain by grain, your bitter coffee transforms into something sweet. But no single grain seems responsible for the change. The sweetness emerges gradually, like dawn slowly brightening the sky. Consider your age. When did you stop being young? Your bank account. When did you become wealthy or poor? Your knowledge. At what moment did you become smart? These transitions happen so gradually that your mind can't capture the precise instant of change. Language creates artificial boundaries in a world of smooth gradients. Your brain grows peacefully confused, trying to find sharp edges in nature's gentle slopes. Reality flows like water, while words demand solid containers. The grandfather paradox. Time travel movies always make it look so simple. Hop in your machine, zip back to the past, change history, return home. But science fiction writers discovered a brain-melting problem that makes every time travel plot collapse like a house of cards. Imagine traveling back to 1955 and accidentally preventing your grandparents from meeting. Maybe you distract your grandfather at the crucial moment he was supposed to ask your grandmother to dance. No dance, no romance, no marriage. Without their relationship, your parents are never born. Without your parents, you never exist. But wait, if you never existed, who traveled back in time to prevent their meeting? Without disrupting the timeline, your grandparents meet normally, fall in love, and eventually create the family line that leads to you. So you do exist, which means you can travel back and disrupt their meeting again. Your mind starts spinning in that familiar loop now, doesn't it? Like being trapped in a revolving door that turns both directions simultaneously. Cause and effect chase each other's tails in an endless, dreamy circle. Scientists call this a causal loop, events causing themselves in impossible ways. Every science fiction writer eventually faces this puzzle. Create elaborate rules to prevent paradoxes, or accept that time travel stories exist in a realm where logic takes a peaceful nap. Reality might be stranger than fiction, but at least it doesn't tie your brain in temporal knots. Your thoughts drift like leaves caught in circular winds. The bootstrap paradox. Shakespeare's greatest plays might have been written by Shakespeare himself, traveling back in time. This mind-bending loop creates something from nothing, like pulling yourself up by your own bootstraps, hence the name that makes physicists smile and philosophers weep. Picture this impossible scenario. You travel back to 1600 London and discover young William Shakespeare struggling with writer's block. Being a helpful time traveler, you recite Hamlet from memory, the same version you learned in school. Shakespeare frantically scribbles down every word, publishes the play, and becomes the legendary playwright. History remembers. But wait, where did Hamlet actually come from? You learned it from Shakespeare's published works. Shakespeare learned it from your recitation. The play exists without ever being created, a literary ghost haunting the timeline. Information loops create themselves in the strangest ways. A brilliant inventor travels back in time and meets her younger self, sharing the blueprints for the time machine. The younger version builds the machine using those plans, grows up, travels back, and gives herself the same blueprints. The invention has no origin point, Dio. It simply exists in an eternal circle. Modern physics calls these closed, time-like curves, paths through space-time that curve back on themselves, like a river that somehow flows into its own source, creating water from nothing while your rational mind slowly dissolves. Musicians, writers, and inventors throughout history might be borrowing from their own future selves without knowing it. Creativity becomes a snake, eating its own tail in the gentlest possible way. Schrödinger's cat. Inside, a sealed steel box sits the most famous feline in scientific history, simultaneously alive and dead until someone dares to peek inside. Austrian physicist Erwin Schrödinger created this thought experiment in 1935 to expose the absurdity of quantum mechanics, but accidentally gave birth to the most mind-bending paradox in modern science. Picture a diabolical contraption that would make any cat owner's heart race. A Geiger counter monitors a tiny piece of radioactive material, Uni-I, so small that within 1 hour, there's exactly a 50% chance a single atom will decay. If decay happens, the counter triggers a hammer that smashes a flask of poison, killing the unfortunate cat. If no decay occurs, the cat remains peacefully alive. Common sense whispers that, before opening the box, the cat must be either alive or dead, one or the other, right? Quantum mechanics laughs at your common sense and insists something far stranger occurs. According to the mathematical laws governing atomic behavior, that radioactive atom exists in what physicists call superposition, simultaneously decayed and not decayed until observed. Since the cat's fate depends entirely on the atom's state, quantum theory demands the cat also exists in superposition, NEU, neither fully alive nor completely dead, but somehow both at once. Your logical mind recoils from this impossibility. How can something be alive and dead simultaneously? Yet every quantum experiment confirms this bizarre reality at the microscopic level. Electrons spin clockwise and counterclockwise at the same time. Photons pass through multiple slits simultaneously. The universe operates on principles that make your brain feel like warm honey. Schrödinger designed this paradox to highlight the weirdness of applying quantum rules to everyday objects. He wanted to show how ridiculous it would be if quantum superposition affected things larger than atoms. Instead, he accidentally described what many physicists now believe actually happens. Reality itself remains undefined until consciousness collapses the possibilities into a single outcome. Modern interpretations suggest multiple universes branch at each quantum decision. In one universe, you open the box to find a living cat. In another, you discover the tragic opposite. Both realities exist simultaneously until your observation forces the universe to choose which timeline becomes real for you. Consider how this applies to your daily decisions. Before checking your phone for messages, do those texts exist in a superposition of sent and unsent until you observe them? When you flip a coin, does it spin through all possible outcomes until gravity forces reality to pick heads or tails? Your smartphone's processor relies on quantum tunneling, as electrons, literally disappearing from one location and reappearing somewhere else without traveling the space between. The device you're watching this on operates using principles that classical physics says should be impossible. Sleep scientists studying consciousness face similar paradoxes. When does your aware mind transition into unconscious sleep? Like Schrödinger's cat, Awareness seems to exist in multiple states, simultaneously: awake, drowsy, dreaming, deep sleep, until morning. Observation collapses the night into memory. The gentle absurdity wraps around your thoughts like a quantum blanket, soft and impossible at the same time. The twin paradox. Across the universe, identical twins face an impossible choice that will age one faster than the other. Einstein's theory of relativity predicts something that sounds like pure science fiction. It slows travel at near light speed, and time itself slows down around you. Meet two identical twins celebrating their 30th birthday together. One decides to become an astronaut, boarding a spacecraft capable of traveling at 90% the speed of light. The other stays home, living a normal Earth-bound life. Both expect to reunite when the space traveler returns after what feels like a 10-year journey. Mathematics reveals something mind-bending about their reunion. While the Earth-bound twin experiences every single day, week, and month of those 10 years, aging normally from 30 to 40, the traveling twin experiences time moving much slower. What feels like 10 years in space equals roughly 4.4 years of aging for the space traveler. When they reunite, the astronaut twin returns looking 35 years old, while their Earth-bound sibling appears 40. Same genetics, same starting age, yet one twin aged slower simply by moving really fast through space. Your smartphone's GPS satellites experience this effect right now. They orbit Earth at high speeds, causing their internal clocks to run slightly slower than clocks on the ground. Without constant adjustments for this time difference, your GPS would place you several miles away from your actual location within hours. Commercial airline pilots actually age microseconds slower than ground-based people due to their constant high-speed travel. The effect is tiny, gaining maybe an extra nanosecond of youth per flight, but Einstein's equations prove it's happening. Even stranger. From the traveling twin's perspective, Earth appears to be moving away at high speed, which should make the Earth-bound twin age slower. Both twins can claim the other is the one truly moving, creating a paradox within the paradox. Time becomes elastic when speed approaches light, stretching and compressing like a rubber band made of moments. The Monty Hall problem. Behind three identical doors on a television game show lies one of probability's most brain-melting puzzles, one that makes mathematicians argue and audiences scratch their heads in bewildered confusion. Picture yourself as a contestant on Let's Make a Deal. 3 doors stand before you. Behind one door sits a shiny new car. Behind the other 2, well, let's just say goats aren't exactly the prize you're hoping for. The host asks you to choose door number 1, 2, or 3. You confidently pick door number 2. Simple math tells you there's a 1 in 3 chance, roughly 33%, that you've chosen correctly. The other 2 doors split the remaining 67% probability between them. Now comes the twist that breaks most people's brains. The host, who knows what's behind each door, opens door number 3 to reveal a goat. Suddenly, only 2 doors remain unopened, yours and door number 1. The host offers you a choice: stick with your original pick or switch to the remaining door. Your intuition screams that it doesn't matter. 2 doors, 1 car. IF. Surely, it's a 50-50 chance either way. Your logical mind feels comfortable with this reasoning, until mathematics proves your intuition completely wrong. Switching doors actually doubles your chances of winning. When you first chose door number 2, you had a 33% chance of being right and a 67% chance of being wrong. Opening door 3 doesn't change those original odds. It just reveals where that 67% probability now lives. Television producers discovered this paradox, drives audiences crazy. Even mathematicians initially argued about the correct answer. Paul Erdős, one of history's greatest mathematical minds, refused to believe the solution until someone showed him computer simulations proving the math. Your brain rebels against this answer because it feels like the host's action shouldn't matter. Yet, revealing new information fundamentally changes the probability landscape. Like turning on lights in a dark room and discovering the furniture has moved. Decision-making in real life mirrors this confusion constantly. Should you switch jobs when a better offer appears? Change your restaurant order when the waiter mentions a special? Your mind assumes all options remain equal, but new information shifts the odds in invisible ways. Probability becomes a magician, performing tricks your intuition can't catch. The birthday paradox. Within any group of just 23 random people, something magical happens that defies every instinct your brain possesses about probability. Two people will almost certainly share the same birthday. Walk into your office break room, count 23 co-workers, and mathematics insists there's a 50.7% chance that at least two of them celebrate their birthday on the exact same day. Most people's intuition screams this can't be right. After all, there are 365 days in a year. Shouldn't you need way more people? Your logical mind probably thinks you'd need around 183 people. FSA day, roughly half of 365 FSA, to get even odds of a birthday match. But probability works in wonderfully weird ways that make your brain feel like it's swimming through honey. Instead of asking, "What's the chance someone shares my specific birthday?" the paradox asks a different question entirely. What's the chance any two people share any birthday? Suddenly, you're not comparing 22 other people to your single birthday, every papacy. You're comparing every possible pair of people to each other. With 23 people, you're actually making 253 different birthday comparisons. Person A compared to persons B through W. Person B compared to persons C through W. The combinations multiply faster than your sleepy mind can track. Soccer teams experience this constantly. With 23 players on most professional rosters, birthday twins appear so frequently that coaches stopped being surprised. Your high school graduating class likely had multiple birthday pairs, even though nobody thought to check. Facebook's data scientists confirm this paradox affects millions of friend groups daily. Dating apps use similar probability principles to match people, knowing that seemingly unlikely connections happen far more often than users expect. Social media algorithms exploit your birthday paradox blindness by showing you coincidental connections that feel magical but are actually mathematically predictable. Random chance creates patterns that feel impossibly meaningful, like finding constellations in cosmic chaos. Hilbert's Hotel. Imagine checking into a hotel with infinitely many rooms, every single room occupied. Yet somehow, there's always space for one more guest. German mathematician David Hilbert created this mind-bending thought experiment to explore the strange mathematics of infinity. Welcome to the Grand Hilbert Hotel, where no vacancy signs become meaningless. Every room, from 1 to infinity, currently houses a guest. Age D. Millions, billions, trillions of travelers, stretching endlessly down impossibly long hallways. The night manager assures you they're completely booked, then cheerfully offers you a room anyway. How does impossible hospitality work? Simple. Ask every current guest to move from their room to the next room number. Guest in room 1 moves to room 2. Guest in room 2 moves to room 3. Everyone shifts one room higher, like an infinite conga line of luggage and confusion. Suddenly, room 1 sits empty and ready for your arrival. Mathematical magic just created space from nowhere, accommodating you without displacing anyone permanently. But wait, it gets stranger. What if an entire tour bus arrives with infinitely many new passengers? No problem for our mathematical hotel manager. Ask all current guests to move to rooms with even numbers. Room 1 to room 2, room 2 to room 4, room 3 to room 6. Now every odd-numbered room stands empty, ready for infinite new arrivals. Infinity plus infinity still equals infinity, breaking every rule your brain learned about addition in elementary school. Real-world applications appear in computer science constantly. Digital storage systems manage infinite data streams using similar principles, creating space by reorganizing existing information rather than requiring physical expansion. Internet servers handle unlimited user requests by redistributing processing loads, much like our hotel shuffling guests between rooms. Your streaming service never runs out of bandwidth using mathematical tricks that mirror Hilbert's hospitality. Even your dreams operate on infinite hotel logic, adding new experiences without discarding old memories, expanding consciousness without requiring additional mental space. Infinity becomes a lobby that never fills, no matter how many travelers arrive seeking rest. The Banach-Tarski paradox. Mathematics discovered a way to turn one orange into two identical oranges without adding any new fruit, using nothing but impossibly precise cuts and otherworldly reassembly techniques that make your logical mind melt, like this. Warm butter. Polish mathematicians Stefan Banach and Alfred Tarski proved something that sounds like pure magic in 1924. Take any sphere. Imagine a perfect orange sitting on your kitchen counter. Using mathematical precision that exists only in theory, slice this orange into exactly 5 pieces, using cuts so intricate they defy physical reality. Now comes the impossible part. Rearrange these 5 pieces into 2 complete oranges, each identical in size and volume to your original fruit. No stretching, no adding material, no cheating. Pure mathematical reorganization that doubles your orange supply from thin air. Your brain probably feels like it's swimming through honey right now, struggling to grasp how one thing becomes 2 things without any addition. The secret lies in something mathematicians call non-measurable sets, pieces so geometrically complex that normal rules of volume and measurement simply break down. These theoretical cuts slice through space itself at impossible angles, creating fragments that exist in mathematical dimensions your everyday experience can't comprehend. Each piece contains infinite internal complexity, like fractals that branch endlessly inward. Physical reality prevents this paradox from working with actual oranges, atoms, quantum mechanics, and the fundamental structure of matter impose limits that pure mathematics gleefully ignores. You can't walk into your kitchen and double your fruit supply using theoretical geometry. Computer graphics programmers encounter similar infinity puzzles when rendering 3-dimensional objects. Digital shapes can be manipulated in ways that would be physically impossible, creating virtual worlds where mathematical rules override natural laws. Pure mathematics lives in a realm where logic becomes poetry, and impossible transformations feel as natural as breathing. Gabriel's horn. Between finite and infinite lies a mathematical shape that painters dream about and mathematicians lose sleep over. A trumpet that extends forever, yet somehow contains only a limited amount of paint. Picture Gabriel, the biblical angel, preparing to sound the final trumpet. His horn stretches infinitely into the distance, growing thinner and thinner as it extends toward eternity. Mathematicians call this shape Gabriel's horn, or the Torricelli trumpet, a geometric wonder that breaks every rule your intuition knows about space. Calculate the volume inside this infinite trumpet, and mathematics delivers a shocking answer, exactly pi cubic units. Despite stretching endlessly outward, the horn contains finite space, in container, like a cosmic container with measurable capacity. But try to paint the outside surface of Gabriel's horn, and you'll face an impossible task. The surface area extends infinitely. No amount of paint could ever cover the entire exterior, even though the interior volume remains perfectly finite. Your brain probably feels that familiar spinning sensation now. How can something have infinite outside but finite inside? Imagine trying to fill this trumpet with water. You'd need exactly pi units of liquid, yet painting the same trumpet would require infinite gallons of paint. Real-world applications appear in engineering constantly. Satellite dishes, telescope mirrors, and speaker cones all use similar mathematical principles, focusing infinite signals into finite spaces, or projecting finite sounds across infinite distances. Medical imaging technology relies on comparable geometry when CT scanners collect infinite data points to create finite three-dimensional images of your body. Infinite information compressed into manageable digital files. Even your smartphone antenna captures radio waves using horn-shaped designs that channel infinite electromagnetic signals into finite electrical currents. Mathematics reveals that infinity and finiteness can coexist in the same object, like measuring the coastline of a dream. The omnipotence paradox. Can an all-powerful being create a rock so heavy that even they cannot lift it? This ancient question has puzzled theologians, philosophers, and anyone who's ever wondered about the limits of unlimited power. Logic creates an impossible trap around the concept of omnipotence. If a supreme being can create such a rock, then there exists something they cannot do, lift that rock, which means they're not truly all-powerful. But if they cannot create the rock, then again, there's something they cannot do, proving they lack omnipotence. Medieval scholars spent centuries wrestling with this paradox, trying to protect their concept of divine perfection from logical contradiction. Some argued that omnipotence doesn't include the power to create logical impossibilities, like square circles or married bachelors. Your smartphone demonstrates a similar limitation paradox in computing. Can a computer program create a password so complex that the same computer cannot crack it? Modern encryption relies on this principle. NE10. Your device generates codes that would take billions of years for identical hardware to break. Video game developers face omnipotence paradoxes constantly when designing all-powerful characters. Can a God mode player create an obstacle they cannot overcome? Game designers solve this by limiting divine power within specific rule systems to omnipotence, bounded by programming constraints. Even your imagination encounters this paradox. Can you conceive of something you cannot conceive? The moment you think about unthinkable concepts, you've already thought them, making them thinkable by definition. Philosophy suggests that omnipotence might be self-limiting. True ultimate power includes the power to restrict itself. Like a master key that can lock doors, it cannot reopen. Power becomes paradoxical when it approaches infinity, long, 2id, strength that defeats itself through its own limitless nature. The crocodile dilemma. Ancient Egypt presents a mother with the most twisted bargain imaginable. A crocodile has snatched her beloved child and offers one chance at rescue through a deadly game of logic. Picture yourself standing beside the murky Nile River, heart pounding as massive jaws hold your most precious treasure. The crocodile speaks with surprising eloquence. Predict correctly what I will do, and I'll return your child safely. Guess wrong, and, well, dinner is served. Your mind races through the possibilities. Say, you will return my child. And the crocodile faces an interesting decision. If it planned to return the child anyway, your prediction proves correct, so the child comes home safely. But if it intended to keep the child, your wrong prediction means it gets to follow through with its original plan. Seems straightforward enough. until you consider the alternative prediction. What happens if you boldly declare, "You will not return my child"? Now, the crocodile's reptilian brain starts overheating. If it returns the child, your prediction was wrong. Meaning, by the rules, it should keep the child. But keeping the child would make your prediction correct. Meaning, it should return the child. Logic traps the crocodile in an endless loop. Return the child because the prediction was right, but that makes the prediction wrong. Keep the child because the prediction was wrong, but that makes the prediction right. Ancient philosophers used this dilemma to explore promises, predictions, and the strange relationship between words and actions. Medieval scholars debated whether clever paradoxes could actually force outcomes in real situations. Modern contract law faces similar puzzles when agreements contain self-referential clauses. Legal documents sometimes create logical impossibilities that courts must untangle using practical wisdom rather than pure logic. Your brain probably feels that familiar gentle spinning now, logic chasing its tail in crocodile-infested waters. The unexpected hanging paradox. In a courthouse somewhere, a judge delivers the strangest death sentence in legal history, not sighed, announcing that an execution will occur next week on an unexpected day, catching the condemned prisoner completely by surprise. Picture yourself in that cold prison cell, frantically trying to deduce when your final day will arrive. Your logical mind starts working through the possibilities with mathematical precision. Could the hanging happen on Friday? Impossible. If you make it to Thursday night alive, you'd know with certainty that Friday must be the day. No surprise there. What about Thursday then? Again, your reasoning mind objects. If Wednesday passes without incident, and you've already ruled out Friday, Thursday becomes predictable, not unexpected at all. Wednesday suffers the same logical fate. Eliminate Thursday and Friday from consideration, and Wednesday becomes obvious by Tuesday evening. Your deductive reasoning continues this backwards chain until every possible day seems predictable. By this ironclad logic, no day next week can truly surprise you. Monday fails because, having eliminated every other option, it becomes the only possibility remaining. Your mind relaxes, convinced the judge's sentence contains an impossible contradiction. Monday morning arrives, and so does the executioner. Complete shock floods your final moments. The hanging genuinely caught you off guard, despite your careful logical analysis. The unexpected execution proves itself possible by actually happening, making your reasoning both perfectly logical and completely wrong. Philosophers call this a prediction paradox, self-referential statements that defeat themselves through their own logic. Weather forecasters face similar puzzles when predicting unexpected storms or surprise temperature drops. Your brain feels that familiar gentle confusion now, logic that seems airtight, yet fails catastrophically when reality arrives. Mathematical certainty dissolves like morning mist when paradoxes step out of theory into the real world. Simpson's paradox. Statistics can lie even when every number tells the absolute truth, creating impossible scenarios where success rates increase and decrease simultaneously, depending on how you group the data. Consider two emergency room doctors competing for the hospital's Best Success Rate award. Dr. Smith saves 83% of patients, while Dr. Jones manages only 78%. Clear winner, right? Dr. Smith deserves that award until someone examines the data more carefully, break down their cases by severity, and something mind-bending emerges. For minor injuries, Dr. Smith saves 87% of patients, while Dr. Jones saves 95%. For critical cases, Dr. Smith manages 73%, while Dr. Jones achieves 77%. Somehow, Dr. Jones performs better in both categories, yet worse overall. Your brain probably feels like it's swimming through statistical honey right now. How can someone win every battle but lose the war? The answer lies in hidden variables that skew the overall picture. Dr. Jones treats mostly difficult cases, 80% critical patients, and only 20% minor injuries. Dr. Smith sees the opposite ratio, mostly easy cases, with excellent survival rates. When combined, Dr. Smith's abundance of easy wins creates a misleading overall average. Baseball statistics reveal this paradox constantly. Player A might have a higher batting average than player B in every month of the season, yet somehow finish with a lower average overall. The magic happens in the number of at-bats during different months. College admission data frequently demonstrates Simpson's paradox. Universities can show higher acceptance rates for every demographic group individually, while maintaining a lower overall acceptance rate than competitors. The enrollment mix creates statistical illusions that fool casual observers. Your social media engagement rates probably experience this paradox daily, posting more successfully on weekdays versus weekends, yet showing lower monthly averages due to timing patterns. Numbers become magicians, making truth disappear through perfectly honest statistical sleight of hand. The Fermi paradox. Across 13.8 billion years of cosmic history, our universe should be teeming with alien civilizations, yet somehow we appear completely alone in an impossibly vast and silent cosmos. Enrico Fermi asked the question that still haunts astronomers today: where is everybody? Consider the mind-boggling numbers involved. Our galaxy contains over 100 billion stars, many with planetary systems. Billions of these worlds exist in habitable zones where liquid water could support life. Even if life emerges on just 0.01% of suitable planets, millions of civilizations should exist in our galaxy alone. Some would be millions of years more advanced than humans, capable of interstellar travel, massive engineering projects, or communication signals that span light years. Yet when we scan the heavens with our most sensitive instruments, we find nothing. No radio signals, no megastructures, no evidence of intelligence beyond Earth. The cosmic silence feels deafening. Several explanations compete to solve this puzzle, each more unsettling than the last. Perhaps intelligent life inevitably destroys itself before achieving interstellar travel. Nuclear weapons, climate change, or artificial intelligence might represent universal great filters that civilizations cannot survive. Maybe advanced aliens practice strict non-interference, observing primitive species, like us, from a distance without making contact. We could be living in a cosmic zoo where more developed beings study our behavior while remaining invisible. Or perhaps we're genuinely alone, the first and only intelligent species to emerge in our galactic neighborhood. Earth's specific combination of factors might be so incredibly rare that consciousness represents a 1 in a trillion accident. Your smartphone contains more computing power than entire space agencies possessed when Fermi first posed this question. Yet our searches continue finding empty silence where bustling civilizations should exist. The paradox transforms every starry night into a philosophical mystery. Olbers' paradox. Every clear night sky presents one of astronomy's most beautiful mysteries. Why does darkness exist at all, when infinite stars should flood the universe with blinding light? German astronomer Heinrich Olbers posed this question in 1823 while gazing up at the star-filled heavens. His logic seemed flawless. If the universe contains infinite stars distributed evenly throughout infinite space, then every direction you look should eventually hit a star's surface. Picture standing in the middle of an endless forest. No matter which direction you face, your line of sight eventually encounters a tree trunk. Similarly, every point in the night sky should glow with starlight. making nighttime as bright as day, turning the entire heavens into one continuous sheet of stellar fire. Yet, obviously, night remains dark. Stars appear as tiny points of light, separated by vast gulfs of blackness. Your bedroom stays comfortably dim for sleeping, instead of blazing like the surface of the Sunday. Several solutions compete to explain this cosmic contradiction. Perhaps the universe isn't infinitely old, too light from distant stars, simply hasn't had enough time to reach us yet. If the universe began 13.8 billion years ago, we can only see stars within that light travel distance. Cosmic expansion provides another answer. As space stretches between galaxies, light from distant stars gets redshifted. Wavelengths stretch beyond visible light into invisible infrared radiation. The most distant starlight becomes too redshifted for your eyes to detect. Interstellar dust clouds absorb and scatter starlight, creating dark lanes that block our view of background stars. These cosmic smoke screens prevent infinite stellar brightness from reaching Earth. Modern light pollution ironically demonstrates Olbers's paradox in reverse. City lights create artificial daylight that drowns out natural starlight, proving how easily brightness can overwhelm darkness when sources multiply. Darkness becomes a cosmic gift, evidence of a universe with limits, age, and the gentle mysteries that make sleep possible. Maxwell's demon. Between the fundamental laws of physics lurks a tiny, hypothetical creature capable of breaking the second law of thermodynamics, chinking, sorting hot molecules from cold ones with supernatural precision. Scottish physicist James Clerk Maxwell imagined this microscopic demon in 1867 as a thought experiment about entropy. Picture a sealed container divided by a wall with one tiny door. Gas molecules bounce randomly throughout both sides, creating uniform temperature through natural mixing. Now station Maxwell's demon at that door, a being so small and quick it can observe individual molecules approaching. When fast-moving hot molecules approach from the left side, the demon opens the door, allowing them into the right chamber. When slow-moving cold molecules approach from the right, it lets them pass leftward. Gradually, without adding any energy to the system, the demon sorts molecules by temperature. The right side grows blazing hot, while the left side becomes freezing cold, creating a temperature difference from nothing, apparently violating the fundamental law that says entropy always increases. Your refrigerator performs similar work by pumping heat from inside to outside, but requires electrical energy to operate. Maxwell's demon seems to accomplish the same feat, using only information about molecular speeds. Modern computer science revealed the demon's secret energy cost. Observing and remembering molecular information requires energy expenditure. Demon must forget previous observations to make room for new data, and forgetting information generates heat that restores universal entropy. Quantum mechanics adds another twist. The act of observing molecules changes their behavior, making perfect sorting impossible at the microscopic level. Information itself carries an energy cost that your brain experiences every time you process thoughts, turning mental sorting into physical work. The information paradox. Black hole. Within the event horizon of every black hole lies information that physics says cannot be destroyed, yet somehow vanishes completely when the black hole evaporates through Hawking radiation. Picture yourself watching a book fall into a black hole. According to Einstein's relativity, you'd see the book slow down as it approaches the event horizon, its image growing redder and dimmer until it fades from view. From your perspective, the book never quite crosses that boundary, posture, frozen forever at the edge of oblivion. But quantum mechanics tells a different story. Stephen Hawking discovered that black holes slowly evaporate by emitting radiation, CS particle, pairs created at the event horizon, where one particle escapes while its partner falls inward. Over trillions of years, This process completely eliminates the black hole. Your book's information faces an impossible choice. Relativity insists the information remains trapped at the event horizon, preserved but unreachable. Quantum theory demands that information cannot be destroyed, light. It must somehow escape in the Hawking radiation. Yet the radiation appears completely random, containing no trace of your fallen book. Modern physicists propose mind-bending solutions. Maybe information gets encoded on the black hole's surface in ways we cannot detect, like cosmic data storage written in the curvature of space-time itself. Perhaps the information escapes through quantum entanglement between particles inside and outside the event horizon. Your smartphone demonstrates similar information paradoxes when files get permanently deleted. The data seems gone forever, yet forensic experts can sometimes recover supposedly erased information from quantum traces left in memory circuits. Computer scientists face analogous problems when designing secure deletion protocols, EAS, ensuring sensitive data truly disappears without leaving recoverable quantum fingerprints. Information becomes ghostly at the cosmic scale, DSI, simultaneously preserved and destroyed, trapped and free. The prisoner's dilemma. Two accomplices sit in separate jail cells, unable to communicate, facing identical offers from police detectives. KB Phil. Betray your partner or stay silent, with your fate depending entirely on what the other person chooses. You've been arrested alongside your partner in crime. Police have enough evidence for minor charges against both of you, but need confessions to secure major convictions. The detective slides a piece of paper across the interrogation table, outlining your options with mathematical precision. If you both stay silent, you each get 1 year in prison. If you both confess, you each receive 3 years. But, and here's where your logical mind starts spinning, if you confess while your partner stays loyal, you walk free while they serve 5 years. The same deal applies in reverse. Your rational brain immediately recognizes the optimal strategy. Confess every time. No matter what your partner chooses, confession offers a better personal outcome. If they stay silent, you get freedom instead of 1 year. If they confess, you get 3 years instead of 5. Yet, following this perfectly logical reasoning creates the worst possible result for both of you, mutual confession, leading to 3 years each. The solution that benefits you individually destroys you collectively. Economics calls this a Nash equilibrium, a stable state where changing your strategy alone cannot improve your situation, even though better mutual outcomes exist. Your daily life presents countless prisoners' dilemmas. Traffic jams happen when everyone chooses the fastest individual route, creating collective slowdowns. Online reviews suffer when people rely on others' ratings without contributing their own experiences. Climate change represents a global prisoner's dilemma. Roads in individual countries benefit from polluting, while others reduce emissions. Yet universal cooperation yields the best outcome for everyone. Cooperation becomes paradoxically illogical, yet absolutely essential for mutual prosperity. The paradox of thrift. Saving money represents one of life's most responsible financial decisions. Yet, when everyone saves simultaneously, the economy can collapse into recession, making everyone poorer despite their virtuous behavior. Picture yourself deciding to save more money next month. Completely rational choice. You'll have extra cash for emergencies, future purchases, or retirement planning. Your bank account grows while your financial stress shrinks. Personal finance experts universally praise this wise decision. Now imagine everyone in your town making the same choice simultaneously. Suddenly, local restaurants see fewer customers. Retail stores experience plummeting sales. Entertainment venues struggle to fill seats. Businesses start laying off workers as revenue disappears. Your logical mind expects collective saving to strengthen the community. More money in banks should mean more lending, more investment, more prosperity. Instead, the opposite occurs. Reduced spending triggers business failures, unemployment rises, and ironically, everyone becomes less able to save as incomes decline. John Maynard Keynes identified this economic paradox during the Great Depression. Individual thrift becomes collectively destructive when practiced universally, like everyone rushing toward the same exit during an emergency, creating dangerous bottlenecks. Modern economic policy constantly battles this paradox. Government stimulus programs essentially pay people to spend rather than save, counteracting natural thrift instincts during downturns. Central banks lower interest rates to discourage saving and encourage spending. Your personal budget decisions ripple through interconnected economic systems in ways that defy individual logic. Spending becomes patriotic during recessions, while saving gets discouraged despite being personally wise. Holiday shopping seasons demonstrate this paradox annually. Retailers depend on consumers abandoning thrift temporarily to maintain economic stability. Virtue becomes vice when everyone practices it simultaneously, creating prosperity through apparent irresponsibility. Brace's paradox. Adding more roads to reduce traffic congestion can actually make every driver's commute longer, transforming highway improvements into mathematical nightmares that punish well-intentioned urban planning. Picture your daily drive to work through a city with two main routes. Route A takes you through downtown, normally 45 minutes during rush hour. Route B winds through residential areas, also 45 minutes when crowded. Traffic splits evenly between both paths, creating predictable commute times. City planners decide to help by building a new highway connector, AT-Fast, a fast link between the two routes that should give drivers more flexibility. Logic suggests this additional option will reduce overall travel time by providing an escape route when one path gets congested. Instead, something mind-bending occurs. Every driver now faces a tempting shortcut opportunity. Rather than committing to one full route, they can start on Route A, jump to the connector when convenient, then finish on Route B. Or vice versa. Your rational mind calculates this mixed strategy should save time. Why stick to one slow route when you can hop between them? But when everyone makes the same logical choice, both original routes become more congested at their connection points. The new highway fills with drivers constantly switching between paths. German mathematician Dietrich Brace discovered that individual optimization can destroy collective efficiency. Each driver selfishly chooses what seems fastest personally, creating worse outcomes for everyone, including themselves. Commute times jump from 45 minutes to over an hour. Real cities have proven this paradox repeatedly. New York temporarily closed 42nd Street to traffic in the 1,990 seconds, expecting chaos. Instead, traffic flow improved citywide. Stuttgart, Germany removed roads from their city center and reduced overall travel times. Your internet connection experiences similar paradoxes when data packets choose routes through network congestion, sometimes making connections slower despite having more pathways available. Individual rationality becomes collective insanity when everyone optimizes simultaneously. The lottery paradox. Believing something won't happen becomes logically impossible when applied to lottery tickets, even though common sense insists you'll never win the jackpot. Consider your local lottery, where 10 million tickets get sold for tonight's drawing. Logic demands that you believe each individual ticket will lose. After all, the odds against any specific ticket winning are 9,999,999 to 1. Perfectly reasonable to think ticket number 1 will lose, ticket number 2 will lose, ticket number 3 will lose. Your rational mind confidently extends this reasoning to every single ticket in the drawing. If you believe each ticket individually will lose, then logically, you must believe all tickets will lose. Yet, obviously, one ticket must win. Mania. That's how lotteries work. Philosopher Henry Kaiberg discovered this paradox while studying rational belief systems. You simultaneously hold two contradictory beliefs. No individual ticket will win, yet some ticket definitely will win. Both beliefs seem perfectly justified by the evidence. Modern decision theory struggles with similar problems constantly. Insurance companies face lottery paradox thinking, when customers believe they'll never need coverage, while knowing some clients definitely will file claims. Stock market investors experience this paradox daily. 2. Convinced their individual picks will succeed, while acknowledging most investments underperform. Each choice feels reasonable in isolation, yet the overall strategy seems contradictory. Medical screening presents lottery paradox dilemmas. You rationally believe you don't have a rare disease, affecting only 1 in 10,000 people, while doctors know some patients in their practice definitely carry the condition. Your smartphone's predictive text demonstrates similar paradoxes by confidently suggesting words while acknowledging uncertainty about your intended message. Rational belief becomes mysteriously irrational when individual certainties combine into collective impossibilities. The Raven paradox. Under the logical rules of scientific proof, observing a white tennis shoe provides exactly the same evidence that all ravens are black as seeing an actual black raven, a conclusion that makes your rational mind feel like it's melting into warm, philosophical honey. Philosopher Carl Hempel discovered this mind-bending problem while studying how we confirm scientific statements. To prove all ravens are black, scientists typically observe ravens and check their color. Each black raven encountered strengthens confidence in the statement, but logic operates by strange rules that defy intuition. The statement, "all ravens are black," equals the logically equivalent claim, "all non-black things are non-ravens." Both statements express identical information using different words. Now comes the part where your brain starts that familiar, gentle spinning. If observing black ravens confirms the first statement, then observing non-black, non-ravens should equally confirm the second statement, every one, and therefore the original claim. Every white shoe, red apple, blue car, or green leaf you encounter represents a non-black, non-raven, apparently providing evidence that all ravens are black. Sitting in your living room, cataloging household objects somehow advances ornithological research without ever seeing a single bird. Your intuition screams this can't be right. How does a white coffee mug tell you anything meaningful about raven coloration? Yet formal logic insists these observations carry identical evidentiary weight. Scientists face this paradox constantly when designing experiments. Does studying non-cancerous tissue in healthy patients provide equivalent evidence about cancer causes as examining tumor samples? Logic says yes, while medical intuition strongly objects. Machine learning algorithms encounter Raven paradox problems when training on datasets, learning about target categories by processing millions of irrelevant examples that technically qualify as confirming evidence. Scientific method becomes beautifully absurd when pure logic meets practical research in the wild. The paradox of fiction. Fictional characters can make you cry, laugh, or lose sleep with worry. Yet your rational mind knows they don't actually exist, creating an impossible emotional response to people who never lived. Picture yourself sobbing during the final scenes of your favorite movie, heartbreaking as the protagonist faces tragedy. Tears stream down your cheeks for someone who exists only as pixels on a screen, portrayed by actors reading scripted lines. Your emotional response feels completely genuine: grief, joy, anger, or fear, washing over you with surprising intensity. Philosophy calls this the paradox of fiction. How can you have real feelings about imaginary people and events? Logically, emotions should require belief. You fear real threats, love actual people, grieve genuine losses. Yet fictional stories trigger identical emotional responses, despite your knowledge that everything is make-believe. Your brain seems to operate on multiple levels simultaneously. One part recognizes the story as fiction. You don't call emergency services when movie characters get injured, or try to warn them about approaching dangers. Another part responds emotionally, as if the events were real: pulse racing during chase scenes, tears flowing during sad moments. Neuroscience reveals your brain processes fictional scenarios using the same neural pathways as real experiences. Mirror neurons fire when watching characters perform actions, creating empathy and emotional connection. Your amygdala doesn't distinguish between real and imaginary threats when generating fear responses. Children demonstrate this paradox most clearly, hiding behind pillows during scary movies, while simultaneously asking for more. They understand the monster isn't real yet, feel genuine terror at its appearance. Video games amplify this paradox by making you the protagonist. You invest hours building relationships with digital characters, feeling accomplishment from virtual achievements, or sadness when game worlds end. The emotional investment feels real, despite the artificial environment. Social media creates similar paradoxes when you develop genuine feelings about online personas, RT people you've never met, yet care about deeply. Reality becomes negotiable when emotions meet imagination in the gentle space between truth and story. The paradox of tolerance. Tolerance, democracy's most cherished virtue, contains the seeds of its own destruction. Yes, creating an impossible choice between protecting freedom and preserving the very system that makes freedom possible. Philosopher Karl Popper posed this dilemma while watching fascism rise across Europe. Should a tolerant society tolerate those who would destroy tolerance itself? Your democratic instincts say yes. Free speech protects everyone, even those with repugnant views. Silencing anyone threatens the foundation of open society. But unlimited tolerance creates a fatal vulnerability. Intolerant groups can exploit democratic freedoms to gain power, then eliminate those same freedoms once they're in control. They use tolerance as a weapon against tolerant people, demanding rights they would never grant to others. Picture a town hall meeting where residents debate, allowing an extremist group to hold rallies. Denying permission seems undemocratic. DSPS. Everyone deserves equal access to public spaces. Yet granting permission enables the group to spread messages that could eventually destroy democratic participation entirely. Your brain encounters this paradox constantly on social media platforms. Should websites allow all viewpoints to foster open dialogue, or remove content that promotes hatred and violence? Both choices feel simultaneously right and wrong. Universities face tolerance paradoxes when deciding campus speaker policies. Academic freedom demands exposure to challenging ideas, yet some speakers advocate for eliminating the very academic freedom that protects their right to speak. Modern democracies struggle with this daily, balancing free speech against hate speech laws, protecting minority rights while respecting majority rule, defending democratic processes from those who would abuse them. Popper concluded that tolerance becomes self-defeating without limits, requiring the paradoxical intolerance of intolerance to survive. Freedom protects itself by restricting freedom in the gentlest possible contradiction. Curry's paradox. Within the structure of formal logic lurks a sentence so cleverly constructed that it can prove absolutely anything, including obvious falsehoods like the moon is made of cheese, or 2 plus 2 equals 5. Logician Haskell Curry discovered this devastating weapon against rational thought. If this sentence is true, then the moon is made of cheese. Your brain probably feels that familiar, gentle, spinning starting already. How can a self-referential statement about truth somehow prove astronomical nonsense? Watch the logical trap unfold step by step. Assume the sentence is true, meaning both parts must be correct. The first part states, "This sentence is true," which matches our assumption. The second part claims, "The moon is made of cheese," which must therefore also be true if the whole sentence is true. But what if the sentence is false? Well, that makes the first part, "This sentence is true," incorrect, which means the entire conditional statement becomes vacuously true in formal logic. When the if part of an if-then statement is false, the whole statement counts as true regardless of what follows. Either way, true or false, the sentence forces you to accept that the moon is made of cheese. Replace "moon is made of cheese" with any statement you want, and Curry's sentence can prove it with identical logic. Your smartphone's autocorrect occasionally demonstrates similar logical loops when trying to predict your intended words, sometimes getting trapped in circular reasoning that produces increasingly bizarre suggestions. Computer programming languages guard against Curry-style paradoxes through type systems and syntax rules that prevent self-referential statements from crashing logical systems. Philosophy calls this an explosion, when contradictions allow you to prove every statement in the universe, rendering logic completely meaningless. Reason becomes its own worst enemy when sentences reference themselves with mathematical precision. The coastline paradox. Measuring the exact length of any coastline becomes impossible the more precisely you try, creating infinite distances along finite shores that make your rational mind feel like it's dissolving into mathematical mist. Walk along any beach with a measuring tape, and you'll discover something that breaks geometry. Measure the coastline in mile-long segments, ignoring small bays and inlets, and you might calculate 100 miles total. Switch to yard-long measurements that follow every curve and rocky outcrop, and suddenly, the same coastline stretches to 150 miles. Keep increasing your precision. Measure around every boulder, 200 miles. Include every pebble, 200-300 miles. Account for each grain of sand, every microscopic indent where water meets land, and the coastline approaches infinite length. Mathematician Benoit Mandelbrot realized that coastlines are fractals, phases, shapes that reveal increasing complexity at every scale of observation. Zoom in on any section, and you discover new curves, tiny peninsulas, and miniature bays that weren't visible before. Your smartphone's GPS demonstrates this paradox when calculating driving directions along coastal roads. Different mapping systems produce different distance measurements for identical routes, depending on their level of detail and measurement precision. Satellites mapping Earth's coastlines face similar problems. EVOS. Higher resolution images reveal increasingly intricate shoreline details that add length to previously measured boundaries. Each technological improvement in imaging makes coastlines appear longer. Stock market graphs exhibit coastline paradox behavior when investors analyze price movements. Daily charts show smooth trends, but hourly data reveals jagged volatility. Minute-by-minute analysis displays even more complex fluctuations. EDS. Infinite detail, hiding within apparently simple patterns. Biology encounters this paradox when measuring cell membranes, lung surfaces, or blood vessel networks, USC, structures that become infinitely complex under microscopic examination. Reality becomes unmeasurable when precision meets the infinite detail, hiding in every natural boundary. The friendship paradox. On average, your friends have more friends than you do, a mathematical certainty that applies to almost everyone, creating impossible social comparisons that make networking feel like a rigged game. Picture scrolling through social media, noticing how connected everyone else seems. Your friends appear to know hundreds of people, attend constant parties, and maintain bustling social lives while you struggle to keep up with a smaller circle. Your brain whispers that you're somehow socially inadequate compared to your more popular friends. Mathematics reveals this feeling is universal and completely inevitable. Sociologist Scott Feld discovered that friendship networks create statistical illusions, popular. People appear in many friend groups simultaneously, skewing everyone's perception of normal social connectivity. Consider your 5 closest friends. Now imagine their friend counts, maybe 50, 30, 80, 40, and 100 friends respectively. Average those numbers, almost 60 friends per person. Meanwhile, you only have those 5 close friends, plus perhaps a dozen casual acquaintances, totaling 17 friends. Your friends average 60 friends while you have 17. The math works identically for almost everyone, because highly connected people get sampled more frequently in social networks. They appear in everyone's friend list, pulling average friend counts upward. Dating apps exploit this paradox mercilessly. The most attractive profiles appear in many people's feeds, creating the illusion that everyone else has access to incredibly desirable partners. Meanwhile, average profiles see these same super popular people repeatedly, feeling inadequate by comparison. Professional networking events demonstrate friendship paradox effects constantly. The most connected attendees seem to know everyone, making other professionals feel isolated despite having perfectly normal professional networks. Social media algorithms amplify this paradox by showing you content from your most active, most connected friends first, creating the impression that everyone else lives more exciting, more social lives. Comparison becomes mathematically unfair when popularity creates visibility, making ordinary social lives feel inadequate against statistically impossible standards. The inspection paradox. At any random moment when you check the bus schedule, you're probably experiencing a longer than average wait time, creating the illusion that public transportation always runs late when mathematics proves you're simply encountering sampling bias. Picture yourself arriving at a bus stop without checking the schedule first. Your rational mind assumes you're equally likely to arrive at any point in the bus cycle, early in the waiting period, middle, or near the end. Logic suggests your average wait should be half the scheduled interval between buses. Instead, something counterintuitive occurs. If buses run every 20 minutes, you'd expect to wait 10 minutes on average, but your actual average wait approaches 15 minutes every T5, significantly longer than mathematical intuition predicts. The paradox emerges from how random sampling interacts with time intervals. Longer gaps between buses create bigger windows for your random arrival. When buses run perfectly on schedule, you're 3 times more likely to arrive during a 30-minute delay than during a 10-minute gap between buses. Your brain experiences this bias constantly without recognizing the pattern. Hospital emergency rooms always seem crowded when you visit, because longer wait times create more opportunities for random patient arrivals to overlap. Short, efficient periods have fewer patients visible at any given moment. Library observations demonstrate inspection paradox effects beautifully. Walk through any library, and you'll notice people reading mostly thick books, not because thick books are more popular, but because readers spend more time with them, increasing your chances of observing them during random visits. Class size surveys reveal this paradox. When students report larger average class sizes than administrators calculate, students experience classes weighted by enrollment, REN, spending more time in bigger classes, while administrators simply average all class sizes equally. Your social media feed exploits inspection paradox principles by showing content from accounts that post frequently, creating the impression that everyone else produces more content than you do. Randomness becomes systematically biased toward longer experiences, making ordinary wait times feel unusually frustrating. The two generals problem. Communication across unreliable networks creates an impossible guarantee that haunts every text message, email, and phone call you've ever sent, proving that perfect coordination between distant parties remains mathematically impossible. Military strategists discovered this paradox while planning coordinated attacks. Picture two armies positioned on opposite sides of an enemy city, preparing a synchronized assault that requires precise timing. Both generals must attack simultaneously. If only one attacks, they'll face defeat. If neither attacks, the opportunity passes. General A decides to attack at dawn and sends a messenger through enemy territory to inform General B. But enemy patrols might intercept the messenger, so General A can't be certain the message arrived safely. Without confirmation, attacking alone means certain destruction. Now comes the part where your logical mind starts that familiar, gentle spinning. General B receives the message and sends back confirmation. Yes, I'll attack at dawn. But this return message might also get intercepted, leaving General A uncertain whether General B knows about the plan. Even if General A receives confirmation, they still worry whether General B knows that General A received the confirmation. Maybe General B thinks their reply was intercepted and won't attack. So, General A sends another message confirming the confirmation, but that message might get lost too. Each message requires its own confirmation, creating an infinite chain of, "Did you get my message that I got your message?" Communications loop endlessly, without ever achieving absolute certainty. Your smartphone demonstrates this problem constantly. When you send a text, you see, "delivered," but did they actually read it? Reading receipts help, but what if the receipt notification failed? Dating apps exploit this uncertainty. Did they ignore your message or never receive it? Internet protocols solve two general problems using good enough solutions: sending multiple copies, setting timeouts, and accepting small risks of miscommunication rather than demanding impossible guarantees. Video calls, online gaming, and streaming services all operate under two general constraints, ever CO. Perfect synchronization remains impossible. So, engineers design systems that work despite communication uncertainties. Perfect coordination dissolves into gentle uncertainty when distance and time create gaps between intention and confirmation. The Sleeping Beauty problem. In a psychology lab, researchers put you to sleep for an experiment that challenges everything you think you know about probability, creating a puzzle where the same coin flip yields different correct answers depending on when you're asked about it. Picture yourself volunteering for this strange study. Scientists explain the protocol. They'll flip a fair coin while you sleep. If heads, they wake you once on Monday and ask about the coin flip result. If tails, they wake you on both Monday and Tuesday, erasing your memory between sessions, so each awakening feels identical. From your perspective, lying in the lab bed Sunday night, the coin has a 50% chance of landing heads, a basic probability that your logical mind accepts without question. Nothing controversial about a fair coin flip, but now imagine waking up in the lab, disoriented and groggy. A researcher asks, "What's the probability the coin landed heads?" Your brain starts that familiar gentle spinning as you realize the situation has changed dramatically. If the coin showed heads, you're definitely experiencing the single Monday awakening. If tails, you could be experiencing either Monday or Tuesday, FRA, both equally likely from your current perspective. Since 2/3 of all possible awakenings occur during tails scenarios, shouldn't the probability of heads be only 1/3? Your rational mind rebels against this conclusion. The coin flip hasn't changed. It's still the same 50-50 chance from Sunday night. Yet your position as an observer creates new information that seems to shift the mathematical landscape. Philosophers split into fierce camps over this paradox. Halfers maintain the probability stays 50%. Coin flips don't change based on observation schedules. Thirders insist awakening creates new evidence that updates the probability to 1/3. Betting scenarios complicate the puzzle further. Would you wager differently on the coin results Sunday night versus Monday morning? Your decision strategy seems to depend on when the question gets asked. Sleep becomes a probability laboratory where time and memory create mathematical mysteries. The doomsday argument. Among all humans who will ever live, you occupy a specific position in the grand sequence of existence, 2R1, and statistician Brandon Carter discovered that your placement might predict humanity's surprisingly near extinction. Picture humanity as a massive theater performance spanning millennia. Every person who has ever lived represents a seat number in this cosmic auditorium. You're sitting in seat number 108 billion or so, counting from the dawn of human history. Your logical mind assumes this performance will continue for millions of years, creating trillions more seats for future generations. But statistical reasoning suggests something unsettling about your position. If humanity truly lasted millions of years more, you'd be sitting in the very earliest rows of an impossibly vast theater, making you extraordinarily special among all humans who will ever exist. Carter's doomsday calculation treats you as a random sample from all humans who will ever live. If 90% of all humans haven't been born yet, then you're among the earliest 10%, too, an unlikely coincidence. Statistical probability suggests you're more likely positioned somewhere in the middle range of human history. Your brain probably feels that familiar gentle confusion now. How can your birth order predict species survival? The mathematics works like estimating total production from a randomly selected product serial number. If you randomly pick item number 1000 from a factory, you'd guess total production is probably a few thousand items, not millions. Modern demographics seem to support this gloomy prediction. The human population has exploded exponentially. More people live today than died in all previous centuries combined. If this growth continues, the next few generations will vastly outnumber all previous humans. Yet something feels wrong about using your existence as statistical evidence for extinction. Climate scientists, medical researchers, and space exploration programs work toward extending human survival rather than accepting mathematical fatalism. Philosophy argues whether random sampling assumptions apply to conscious observers, making predictions about their own species' future. Statistical reasoning becomes existentially unsettling when numbers calculate the lifespan of everything you've ever known. Newcomb's paradox. Before you sit two boxes and an all-knowing predictor who claims to have already determined your choice, creating the ultimate test of whether you believe in free will or accept that your decisions were predetermined long before you made them. Picture yourself in a sterile laboratory facing an impossible decision. Box A contains $1,000, clearly visible through transparent walls. Box B remains opaque, 2,000 Gr. It either contains $1 million or nothing at all. A superintelligent being explains the rules with unsettling precision. You can choose both boxes and take everything, or select only box B and trust in the predictor's accuracy. The twist that makes your rational mind feel like warm honey. This being claims to have studied your psychology, scanned your brain patterns, and already predicted your choice with 99% accuracy. If the predictor believed you'd take both boxes, it left box B empty. If it predicted you'd choose only box B. It deposited $1 million inside. Your decision was apparently made before you even entered the room. Decision theory splits into two camps over this paradox. Two boxers argue that box B's contents are already determined. Taking both boxes can only increase your winnings. The predictor's deposit happened yesterday. Your choice happens now. Logic demands you take everything available. One boxer's counter that the predictor's accuracy rate makes cooperation mathematically optimal. If the being correctly predicted 99 out of 100 previous participants, defying its expectations seems foolish. Trust the process and select only box B. Your smartphone's recommendation algorithms create similar paradoxes daily, too, suggesting content based on predicted behavior, while your choices simultaneously shape future predictions. Are you discovering new interests or following predetermined digital paths? Free will becomes a betting game where the house seems to know your cards before you've even seen them. Sleep arrives like box B, ASR. Mysterious, predetermined by the day's choices, yet somehow still requiring your decision to finally let go. And with that gentle paradox, your journey through impossible logic comes to its peaceful end. Sweet dreams.